new entity.
We have looked at digital systems, and we have, that was a quick review. And because we are going to be talking about testing, and hardware is going to be our example, so that would be useful. And right now we are looking at fault modeling. So basically, we want to see how we can come up with fault models so that if you test for all the faults in the fault model, you would test for as many faults as possible. Now, normally, now, how many of you think that if you are doing something, let us say testing something, how many of you think that you should do 100% of the job? How many of you believe in doing 100% of the job? Now that is a slogan you will encounter frequently, but it turns out that it's an idealistic thing. Finding 100% defects in software is practically infeasible. For hardware, if it's a small one, you could do it for any practical size software. And actually later on, we are going to see something like this. Say, here you have defects. And let's say, and we have some number of defects. Let's say you start with some n defects here, and you want to come down to 0, and you're testing it, then how much effort it will take? Now if you don't do any testing, and if you just still have all the bugs in there, that of course takes no effort. But so is it going to be, do you think it is going to be like this? The amount of effort involved, do you think it will go linearly with the number of defects found? No, actually it turns out that the faults that are left behind, they are the ones harder to test. So actually, your effort really is going to grow exponentially, and coming down to 0 defect, it may be a nice slogan, but in practice coming to 0 defects is practically infeasible in most reasonably sized systems. So basically we want to simplify the problem of testing. You don't want to be testing forever. And so fault modeling is an approach to simplify things. And I was mentioning in hardware, opens and shorts. And then there are some others. They happen to be some of the most common things that can cause defects. And that brings us to the stuck-at model that we had started to look at last time. Basically, here is the model. Model is that any one or more of these may be stuck at 0 or stuck at 1, and these include a gate input. So we are talking about things at the gate level. And a gate output. And a primary input. The primary input is basically an input coming from somewhere outside. So any of these, one or more of these could be stuck at 0 or stuck at 1. And this is the classical stuck at 0, 1 fault model. And of course the justification is, and I'm going to show you why this is justified. So I will give you an example. So we are going to look at some simple things at the transistor level. And I will later show why this actually works in many cases, not all the cases. Now let us define the term test. What is a test? Now we will talk about a test for a specific fault. Now our objective is to see if this particular fault is there or not. And if something is a test, then this test will detect the presence of this fault. So is an input combination. Which results in different outputs. For normal and faulty circuits. Now here we are assuming that we have a circuit. You apply something at the input and you observe the output. And if the output is different from what you expect, then that is a test for a specific fault. And now if it is a combinational circuit, then we have, I was mentioning last time, a test vector, and it is also sometimes called a test pattern, and we are going to see some examples. And then you can have a test set. So sometimes you generate a number of patterns, and you refer to them as the test set. Now you should contrast that for sequential circuits. Where you need test sequences. And then you have sets of test sequences. Testing sequential circuits is a harder challenge. And we will talk about that. Now let us look at an example of the stuck at fault model. So let us assume that we have a circuit. It's a simple example. And this is an example. Let us say we have a circuit. Now in most cases, I'm going to use simple examples, and we could work on bigger examples. The thing is that basically I want to illustrate the basic idea, and once you know the basic idea, then of course you can apply it for bigger example. So it will just take more work, but right now we want to look at the basic idea. And let us assume that the inputs are x1, and here is x2, and here is x3, and let's assume the output is z. And let us pick a couple of nodes. Let's call this node is node A, and this node is node B, and this node is node C. Now notice here, x2 is a primary input, right? Node A is the input of this gate. Node B is the input of this gate. Now, since they are connected together, you might think that they are the same thing, right? And in some cases, they will turn out to be the same thing, but in some cases, there could be a difference. And so let's take a look at this example. Now, here's the normal function. So the normal function for this is basically, as you can see, it is x1, x2 plus x2, x3, right? So that's the normal function. And now let us talk about the faulty functions. Okay, let's assume that line x2 is stuck at 1. Then, what does it imply? That z is equal to what? So this line is stuck at 1, it's always 1. So what can we say about line z? Well, since this is always 1, so this is x1 and this is x3, so this is x1 plus x3, right? So this here is the faulty function. This is a function which corresponds to the case when this fault is present. Any questions on this? Okay, let's look at another example. How about line A stuck at 1? What would you say? In this case, what would be z equal to? This is line A. So notice that here we are not assuming that there is any problem with x2. We are not assuming there is any problem with B. But we are assuming that there's a problem with line A. Now, some of you are electrical engineers here, so you might wonder, how is it possible that this is not affected, this is not affected, but this is affected? Now, keep in mind that A being stuck at 1, that is a model. And we don't exactly know why it is stuck at 1, but for whatever reason. Now, it is possible that there is some fault in here which is causing this line to be stuck at 1. And in that case, this is not affected, this is not affected, but this looks like this is stuck at 1. So, what would happen if A is stuck at 1, then obviously this is x1, and this is still x2 plus x3. Oh, I'm sorry, x2 ANDed with x3. Okay, and for comparison, let us see what would happen if B is stuck at 1. The B is this input. And if B is stuck at 1, this is okay. And that is, so Z is equal to x1, x2 plus x3. So compare these three here. So you can see that the faulty function in the three cases are different. This is a faulty function in this case, faulty function in this case, faulty function in this case. So in general, these faults are not equivalent. They can have a different effect. Okay, now let's do a couple more examples. How about C stuck at 1, which is this internal line. And that would imply that output